So, no calculators allowed for this question. So good thing, because I don't have my calculator with me. We have n of t, and we have n of t for three different scenarios. The first one is from 0 to 6. Then the next scenario is from 6 to 8. And then the last scenario is for anything greater than 8. So when we're looking at these things, we definitely want to focus on one of these three. Did they give us a function? Unless otherwise specified, the domain of f is assumed to be the set of all real numbers x for which f of x is a real number. I wonder. My guess is we probably won't need it, but I'm curious. Oh, yeah, we won't need it. It's funny. All right. So let's take a look. Here's a function, and what n of t is the number of fish in a pond at time t in years is modeled by the function n defined above, where f is a continuous function such that f sub 0 or f of 0 equals 80. It's actually the only thing we will need really in the f of t, because, well, what happens if f of t when t is 1 or 2 or 3? And it actually won't matter. The only one we really will need is 0, and we'll see why in a bit. Okay. So our first question is letter A is asking us to find the limit as t approaches infinity. Well, if t approaches infinity, we have to look at the last function, because this function is the only one that's greater than 8. So everything else is less than 8. So when we're looking at the limit as t approaches infinity, then n of t really is going to be the limit as t approaches infinity of 200 plus 80t over 2 plus 0.05t. There were two different scenarios that I taught in my class. One actually I taught today, but before that we talked about anytime the limit as t approaches infinity, we have what we call function races. In function races, we want the fastest function to get the credit. So what happens is if we have like x squared over e to the x, which function is going to be faster? Is x squared faster than e to the x? Well, when we think about things and you plug numbers in, maybe 2 squared is bigger than e to the 2, but what happens at 100 squared? Well, 100 squared, that's quite a bit. That's 4 zeros, right? So that's 10,000, but what's e to the 100 power? Now that gets incredibly quick, incredibly fast. So when we look at function races, we're looking at which function goes faster. Even this scenario, which function is going to go faster? Just a straight linear curve, or is it going to be a parabola curve? And you know what goes faster, or what reaches infinity much quicker, is going to be the x squared. And that's the one that's going to win the race, which means it's going to be 1 over infinity. 1 over infinity. And we know 1 over infinity goes to 0. So when we look at this, we do have function races. However, today they learned in class about L'Hopital's rule. And what L'Hopital says is if we get, when we plug in our limit, because the first rule of limits is to plug it in. So if I can plug in infinity, wouldn't I get infinity over infinity? And they call this the indeterminate. It means we can't really figure anything out yet. Could have a solution, it might not have a solution. We just don't know at this point. So what we want to do is we want to take the derivative of the top by itself, the derivative of the bottom by itself, then replug our limit in and see if we can get an answer. Okay? That's what L'Hopital's rule says. So if we get infinity over infinity, or you get 0 over 0. And there's a couple others. I think it's 1 raised to the infinity or the infinity raised to the infinity. There's a couple that really aren't seen very often, but could potentially happen. Most of the time, you're going to get infinity over infinity or 0 over 0. And that's when we have to apply L'Hopital, which is taking the derivative of the top, derivative of the bottom, and then plugging our limit back in. And if we do come up with one of these two again, do the process again and keep doing it until we can actually get an answer. So now let's look at the limit as t approaches infinity still. But this time we're going to take the derivative of the top. And the derivative of constant is 0. So we know that just goes to 0. And then 80t, so that's t to the first power. So I'm going to do the power rule, and I'm going to get 80. Same thing down here. Constant is 0. And then the power rule gives me 0.05. So if I'm dividing by a decimal, really it's like multiplying. And if we look at, because remember, we don't have a calculator, we've got to kind of do this freehand. So what I'm going to get is I'm going to get 80 divided by 5 over 100. You're going to go, where did the 5 over 100 come from? Well, because when I'm in the tens, hundredths place, I've got 5 hundredths, which is how I got it. So now I'm going to do 80. I'm going to multiply by the reciprocal. And now I could, well, you could do this as well. Doesn't really matter. Either way you go. I could do 80 divided by 5 or 100 divided by 5. Both answers will get us what we need. Sorry. So I'm going to do 80 times, and I'm going to do this, and I'm going to get 20. And what I'm going to get is 8 times 2 is 16 with, that's not, hold on. I'm jumping ahead of myself. So add the 0, then multiply by the 0, and then get 60. Oh, no, I was right. Okay. 1600. So it says find the limit as t approaches infinity of n of t. A good rule of thumb anytime you have an open response is go back and read the question, because what's going to happen? Explain the meaning in the context of the problem. So as time in years approaches infinity, the number of fish approach 1600. So there is a tapering off point. Maybe there's not enough room, or, you know, overcrowding, whatever it is, it just kind of hits its max. And what its max is going to be is 1600. Excuse me. So when we look at the solution, this one says the student response accurately includes both criteria. Finding the limit, so we did find the limit 1600. As time increases, the number of fish in the pond approaches 1600. Okay, all right, so we're good with that. And remember, if you have any questions, make sure to throw them in the chat. Do whatever you need to do. I want everyone to understand what's going on. So that's part A. Part B is the function n continuous at t equals 8. Justify your answer. So what has to happen when we do this is, as our function comes in, what do we do? As our function comes in from the left-hand side and leaves from the right-hand side, at t equals 8, this value has to be the same for both. This value, I'm going to make it a different color, has to be the same for both the blue and the pink. So the function coming in, and the function coming in is 25t plus 150 And the function leaving is 200 plus 80t over 2 plus 0.05t. And you're going to go, well, where did that stuff come from? And that's a great question. So as we look to the left-hand side, we would get 7, 6, 5, all those numbers, right, as we go. And after it, we're going to get 9, 10, 11. Well, what function, when t is less than 8, should we be looking at? Well, we'll look at it till 6. But remember, our focal point is only at 8. So we look at this function. And then as we go greater than 8, remember our focal point is that function. So what we need to do is we need to do n of 8 for 25t plus 150 and n of 8 for 200 plus 80t over 2 plus 0.505t. All right. Also, remember, once again, we don't have a calculator. I know that's kind of crummy, but unfortunately is our process. I try and take things in terms of money. So if I had 25 cents a quarter, I had 8 quarters, that would be $2, right? If you're unsure, do 25 times 8, and we would get a 40, carry the 4, then 16, 17, 18, 19, 20, and get 200. All right, so n of 8 over here is 350. Not too shabby. Now let's do it over here. This will, I think, be a little trickier one, just because there'll be another step or two. So 80 times 8 over 2 plus 0.05 times 8. Yeesh. Okay. So 80 times 8, we're going to get 200 plus 8 times 0 is 0. 8 times 8 is 64. Then we're going to do 2 plus 8 times 5. So 8 times 5 is 800. So if I move the decimal 2 spots and I move the decimal 2 spots, I'm really doing 800 times 5. 0, 0, 40. And then I had 1, 2 numbers behind the no. Am I screwing up? No, it's got to be this. My bad. Hold on. 0.05 times 8. 0, carry 4, 4, and then there's 2 numbers, so it's got to be 0.4. It has to be 0.4. Man, sometimes, I was just talking about this today too. AP Central is very interesting, and why focus on these basic algebra skills? Is this showing me my calculus knowledge? I'm not sure. And all we're trying to get is it equal to 350. All right. So then we're going to take 840 divided by 240, put 2 more there so we can get rid of that. 2, 4. So we're going to do it 3 times, and that's going to give us 12, 6, 7. Subtract and I'm going to get 1, 2, 0, 0. And then, because I'm going to bring that down, I'm going to do that times 5 maybe. Let's try 5. 0, 20, and 12. So 350. Yuck. It does give me 350 though. So therefore, after doing all this ridiculous math, therefore, because n of 8 less than 8, it's equal to n of 8 greater or equal to 8, makes the function continuous. Whew. Yuck. Now, let's go through and see what this says. Clear those off. All right, so student's response accurately includes all 3 of the criteria below. The limit as t approaches 8 from the left, the limit as t approaches 8 from the right. It's 350, 350, n of 8 equals 350. Yes, n is continuous at t equals 8 because the limit at t approaching 8, n of t equals n of 8. So maybe my limits needed to get in there somewhere. So maybe I needed to do a better job of putting the limit as t approaches 8 from the left and the limit as t approaches 8 from the right, and showing that the limit from t approaching 8 from the left equals the limit t approaching 8 from the right. Therefore, the overall limit exists and the function is continuous. Oof. Man, it's quite a bit though. All right, last one. The function n is continuous at t equals 6. Is there a time t for 0 to t to 6? Ooh, so here we go. A bell should be ringing in your ear right now. That bell should be IVT. Intermediate value theorem. The intermediate value theorem. We are looking for a number n of t, which is 250, and see if there's a value between 0 and 6. So what we need to find is we need to find what n of 0 equals and what n of 6 equals. Well, we already know what n of 0 equals because back at the beginning, it told us f of 0 equals 80. So when we do this, we know n of 0 is f of 0. N of 0 equals 80. Now, n of 6, and because we're equal to 6, this is where we are equal to 6. So we need to use this function, 25t plus 150. So we are going to do 25 times 6 plus 150. 6 quarters equals $1.50 plus $1.50. 6. So 6 equals 300. Now, when doing IVT, n is continuous from 0 to t to 6. And n of 0 equals 80. N of 6 equals 300. So 80 is less than, or let's just do less than 250, which is less than 300. And n of 0 is less than 250, is less than n of 6, or there exists a C value between 0 and 6 where f of C equals 250. And that is building our IVT. And if we look at solution, n is continuous, n of 0 is equal to 80, is less than 250, is less than 300, which is n of 6. That's where I kind of built this thing in. I built the 80, 300, n of 0, n of 6 by the intermediate value theorem. Ooh, so I should say by IVT, there exists a C value between 0 and 6. So I need to use the intermediate value theorem. There must be at least one time t for in between 0 and 6 such that n of t equals 250, which is that final statement, f of c equals 250. I don't think they would have hated it too much, but you definitely want to state by the IVT. So, yeah, I don't know. That didn't go too bad. I hope this all makes sense. If you have questions, leave them in the comments. But AP students, here's another practice FRQ for limits. So yeah.